I keep getting interrupted, so I have to keep stopping the videos. This is grade 12 advanced practice questions. We're continuing on and we're going through this back to the flux stuff again and induced EMF. So over here we have an area and we have a field, and it's initially parallel to the plane of the loop. That's fine. What's happening is it's rotated, so the normal makes an angle. So that means now we have an angle. Originally this field was something like this, and then at the beginning it was parallel to the field, it's parallel to the plane. So the plane being parallel looks like this. The normal might have been like that, perpendicular, but the plane is parallel. The idea here is the starting flux is 0. It's not catching any flux at the beginning. It's then rotated to an angle. It then rotates to an angle, something like this, and this angle is 30 degrees. Now we have an induced EMF. Now there is a change of flux happening in this case. So the change of flux, then we can just do this here right now. Change of flux equals BA cos theta. It should be final minus initial, but the initial is 0, so I only need to do it one time. 0.4 times 3 times cos of 30. Sticking that into your calculator, you should get 1.039, 1.04 Webers. There's the answer there. In this case here, now we're trying to find the speed of this bar. So in this case, we need to pick the formula related to this. If you remember, we obviously have derived them in our actual lesson videos, so I'm going to go ahead and assume that you've watched them and you know what you're doing. The EMF formula will be applied here is BLV. Usually we add sine theta, but this is all 90 degrees. I can ignore the sine theta because sine of 90 is just 1. So BLV, I need V. I can shift solve, rearrange, it doesn't matter. Let's do the shift solve method. No, I'm going to rearrange. Let's do it properly. EMF over BL equals V. So let's stick that over here. I need some more space. The EMF that we have is 5. The B that we have is the field. Here is the field. This is right there. 7.2 times 10 to the minus 3. And then I'm going to multiply that by the length, which is 0.85. 0.85. Okay, sticking this into your calculator, hopefully you will get the correct answer, and that answer should be something like 812 meters per second. 812 meters per second. Didn't give us enough space here. Find the current passing through the resistor. That's just Ohm's law. equals EMF over R. It's the voltage, which is normally a V, but because we have a small v for speed, I don't want to confuse you, or they don't want to confuse you either. That's why we're using EMF instead. It's basically Ohm's law. We have 5 divided by the resistance of 15. 5 over 15, as you might know if you're a math wizard, that will be 0.33. It's a third. 0.33 amps. Draw the direction of the current through the resistor. Okay, so now we're going to have to figure out, first of all, whether the field is getting stronger or weaker. I'm going to use my grip rule to help me get this. So let's try it. So what's happening here is, what is that? It's supposed to be a hand. Anyway, what we're doing, this is going to the left. This area is getting smaller. That means my field is getting weaker. It's getting weaker. If my field is getting weaker, the current doesn't like it. The current's induced field will be in the same direction. Same direction. That means the field induced will be out of the page. And if I point my thumb towards me out of the page, I can see my fingers are curling to the left, clockwise. It's going like this. So it's going to go down through the resistor and up through the bar. So we've drawn the direction of the current, and the arrow was actually there this whole time. I just noticed that. So it's going to be like this. So a way to remember, out is a dot. This is out, and this is always like this. It's always going to be counterclockwise. In is always going to be clockwise every time. So this is out, and this is counterclockwise. This is in, and this is clockwise. So that's something you can just remember if you're doing the out and in, figuring out which way it's going. Done. Amazing. Let's move on. So the table below, for each of the coil positions, identify the EMF as maximum or 0. So the long story short, just to keep it simple, if you're having it completely flat, it is going to be maximum. Vertical is going to be minimum. So that's the easiest way to remember. So if we have it flat, it'll be max. If it's vertical, it's going to be minimum. And if it's flat again, it'll be max again. In the opposite direction, however, it'll be max. So that's just a way, just by looking at the picture, you will know. From that, you can figure out the graphs, which we have. And here we have a graph. Now, let's see, where do we have the vertical position? Vertical position, I've already said to you, is supposed to be minimum. Vertical position will be a minimum EMF, the voltage induced. Okay, well, let's see. Minimum EMF is at 0. 1, 2, and 3. There are 3 points, 4 points where I should see 0. Only one of the points have been labelled as B. So the answer is B here. Maximum, if I asked you, it needs to be in a flat position, which will end up being either A, C, or D. So this is saying a minimum, position 1, because this is vertical. We have our answer. There's a whole long reasoning behind that. I have explained that in my lesson video, so go check it out if you want further clarification. Okay, moving on to a capacitor here. We're trying to find the capacitance. We have an area. We have a distance. We can find the capacitance already. So it's epsilon naught A over D. Epsilon naught A over D. So if you've forgotten what epsilon naught is, don't worry. It is written for you on the front page of your exam. And that is 8.85 times 10 to the minus 12. Multiply that by the area, 0.680, and I'm going to divide all of that by the distance. Millimeters is not good, so I must divide by 1,000. We'll divide that by 1,000, or you can just write 5.5 times 10 to the minus 3. Okay, 8.85, so let's do that. 8.85 times 10 to the minus 12 times 0.680 divided by 5.5 times 10 to the minus 3. And I will get 1.09 times 10 to the minus 9 farads. So 1.09 nanofarads, I would say. But there we go. Next, find the charge on one of the plates. Q equals CV. It's charge on one of the plates. One plate's positive, one plate's negative. That's why they specified one of the plates. It doesn't matter. It's the same thing. You'll get the same value of charge. One will be negative, one will be positive. What's important is finding it. CV, 1.09 multiply by 10 to the minus 9, and I'm going to multiply that by my voltage. Do I have one? Yes, I have. 8 kilo. Kilo means 1,000. This time I'm going to write 8,000 like this, not times 10 to the 3. Putting that into your calculator, hopefully you will get another answer. Let's check. Times 8,000. 8.75. 8.75 times 10 to the minus 6. Minus 6. And what is this charge? This is coulombs. Perfect. All right. So complete the table. When the capacitor is still connected, so I've locked the V in, the V is not changing, what happens to the different things? First things first, as you know, if it's still connected and my voltage is not changing, but I have changed something. What did I do to the distance? The distance is decreased. I brought the plates closer together. That means my capacitance has actually increased. So according to our rule here, the capacitance will increase. Okay. Potential difference across the capacitor. Well, it is still connected to the battery, so this stays the same. Stays the same. The charge stored by the capacitor? Well, like I did in a previous question, if my capacitor has increased, then that means I can store more charge. My charge stored has increased. Energy stored, same thing. It's directly proportional to the charge. E equals a half QV, right? So that's the general formula. You can simply say increased. There we go. So that's what happens if it's still connected to the source. If it's disconnected from the source, the voltage will change and other things will change. I can maybe do that in another video for you if you would like more detail. We can try that. Okay, so what I'm going to do is quickly try and finish off these 3 questions before moving on. 3 capacitors, here we go, are connected as shown. Find the total capacitance. Well, I have these 2 in parallel, and then they are in series with this. The rule for parallel is simply add. I'll do 23 plus 35 23 plus 35, 23 plus 35. That will give me 58. 58. I'm going to now find the total capacitance in series. This is 58. I must use the 1 over rule. 1 over 58 plus 1 over 40. In a bracket, minus 1, same trick works for capacitors as it does for resistors. If I was to put that into my calculator just to speed things along, let's get the answer. It is 24 micro, so 0. All those zeros, 24. 24 microfarads, 24 times 10 to the minus 6. Very nice. That's the total capacitance. Okay, so let's move on. The three identical capacitors are arranged as shown. Okay, what's the total capacitance? So we're going to assume they're all 1, right? Let's just assume that they're 1. 1 and 1. Let's do that. First things first, I need to combine the two. I need to combine them all. I see 2 in series and then they're in parallel with this. I can find out what the series part is and then I can add it to this parallel one. This is 1 over 1 plus 1 over 1 because it's 1 over C plus 1 over C, right? And then that becomes 2 over 1, flipping it, I will get 1 over 2. So that's me doing it without the calculator trick. 1 over 2. You can try it yourself if you like, using the calculator trick of your 1 over 1 minus 1. You will get a half, basically. A half C. 1 over 2 C. Next, I am adding it to this, so I'm adding 1 over 2 C plus a full C. 1 over 2 and a full. That's half and 1. Well, that's 1 and a half, right? 1 and a half is like me saying 1.5. Or if I wanted to make it into a top-heavy fraction, that's 3 over 2. That's 3 over 2c. That's the 3 different ways you can write it. It's in fractions, so 1 and a half is 3 over 2. If you're not good with fractions, you can just think if you had half a pizza, it's Ramadan and I'm hungry, and a full pizza, you have 2 halves. That's me saying I have got 3 halves. 3 over 2. They're split into 2, both of them, and I have 3 of those halves. 3c over 2 or 3 over 2c, same thing. What is the total capacitance? So I need to add them all together, but before I do that, I have these two in series, and that's going to be 1 over or 1 over again. If they're exactly the same, by the way, there's a little trick. This becomes simply half of that. If this is 2, the total will be 1. If this was 4, the total will be 2, and so on. If they're identical, you just divide by the number of resistors. Not resistors, capacitors. So that's 1. 2 plus 1 plus 2. 2 plus 1 plus 2. That's it. 2 plus 1 plus 2 is, of course, 5. And I'm going to stop the video there. It's getting a bit long. I'll move on to the next questions next.